Hey everybody, welcome back to this class. This week we're going to be taking a look at sinusoidal steady state, impedance, and also introducing power briefly. So with that, let's go ahead and get started here. All right, so sinusoidal steady state, impedance, and power. Last week we took a look at alternating current, and so a lot of these waveforms are going to take the form of a sinusoid. Um, And you might be familiar with this idea of Fourier series, which says that we can represent any periodic waveform by a sum of sinusoids. So it makes sense to look at the sinusoidal response to a circuit, generally speaking. So we're going to return to this familiar RC low-pass filter topology, but instead we're going to be driving it with an alternating current source, this voltage source here. We're going to be looking at this drive VI cosine omega t. Right, so we've got our original circuit, and a couple weeks ago we found that the governing dynamics of this circuit is given by RC dVc by dt plus Vc is VI, right? It was originally this input, which was constant, but now we're taking a look at this time varying cosine input. Right, and so just taking a look at this, if you recall, we've got a first order non-homogeneous system. So the first thing that we want to do is look at the particular solution. Right, so when we have this particular solution, and I'm just taking a look at this first because the homogeneous solution is going to be the same result as we found before. But looking at this particular solution, our drive, right, this input is now VI cosine omega t, which is kind of difficult to figure out via our original guess and check method. But what we can do is find the response due to maybe an easier input. So we're going to be taking this input to be VI times e to the st, where s is this j times omega, right? And j is that imaginary number. And so what this allows us to do, if you recall by Euler's formula here, we have this result that says e to the jx is equal to cosine of x plus j times sine of x. And so if we look at the response due to this this new input, vi e to the st, we can take the real part of that response. Right, so this cosine part is the real part. So if we find the real part of this, then it'll give us the solution that we desire here. So we're going to take a look at RC dVcp by dt plus VCP, right? So we're looking at this particular solution to this VI e to the st. And we're going to take this, we're going to assume a form of VCP is this some VCP prime e to the st, which then gives us, right, so the first derivative and s pops out, so we got SRC VCP prime plus VCP prime e to the st is equal to this VI e to the st. And so all these e to the st's, I missed one here, all these e to the st's cancel out. So what we're left with is SRC plus 1, right, times this VCP prime is equal to VI, which gives us then that VCP prime is VI divided by this SRC plus 1, which then gives us, right, so we got to plug that back in here to give us our VCP is VI over SRC plus 1 scaled by e to the st. Right, so there is our particular solution, and taking the real part of this will give us the solution that we desire. I'll just call this, well, it's already called VC, so it's the real part of VCP, right? So VI SRC plus 1 e to the st plus whatever our homogeneous solution is. And I'm going to tell you right now, right? So we had this homogeneous solution. It was of this form. And when we're looking at the steady state, right? So in this case, we're looking at the steady state. We take the limit as time goes to infinity, right? So the time term usually dies out. And that's going to just give us 0, right? So you got that minus t, right? So t is going down. This whole thing is going to 0. So what we're left with is the real part. And just as a refresher, to find this real part, right, we need to, first of all, go back into the complex world. So we're going to take VI times j omega RC plus 1 e to the j omega t. And we're looking at for the real part of this. And to do that, right, we're going to get the complex term out of the denominator here by multiplying by the complex conjugate. So then we're looking at the real part of this expression. So we got VI times this j omega RC minus a VI divided by, and so we got j times omega RC squared, or sorry, not j, so j squared, which will give us a -1. And then we've got a minus j omega RC and then plus a j omega RC, so I'm not going to write that. But then we've got, 1 times -1, so we've got this -1 term. And we're multiplying all this by e to the j omega t. And so we're looking at the real part still of this. Hang on a second. Okay. So we have VI j omega RC minus VI. Oh, well, I'm just rewriting this now. Right, so this exponential has a real part and an imaginary part. So we have to extract that out, but we can cancel, well, let's write it out here. So VI times j omega RC minus VI. And I'm just going to factor out a negative sign here on the bottom to get us this 1 plus omega RC squared. And then we have our times cosine of omega t plus j sine omega t from this, the Euler relation there. Right, so this j sine term goes away when we multiply by VI. Right, so let's pull that guy out. We have a VI cosine omega t from this term here. And then we have a minus VI times this, let's see, we've got j times j, so we're actually adding VI times this sine omega t. And we're also multiplying by omega RC, so omega RC, and we've got 1 plus It's omega RC squared. All right, and so what this boils down to is our VC is now VI over 1 plus omega RC squared times this. We actually have a cosine, right? So this gives us a cosine with some phase shift due to some trig property there. And so where this phase shift is given by the tangent inverse of our negative omega RC. Okay, so that's all fun and good. We're not going to be dealing too much with that. It's just worth, taking a look at it once. So this is the response due to some sinusoidal drive. But what's more important that we take away is looking at the impedance. So when we're talking about impedance, we're looking for the equivalent or the effective resistance of something seen by an alternating current source. So when we have our voltage current relations, right? So we've got V is IR, right, for a resistor. And so the impedance is usually denoted by a Z, and it takes the form, whatever this is multiplying the current or the voltage. And so we look at the sinusoidal current and voltage, right? So we replace V and I with, we multiply through by ST. So then that just gives us V is equal to IR, which means that the impedance of a resistor is just given by R. And so it's this term. So then taking a look at a capacitor, we've got a similar deal. We've got our IC is I is C dV by dt. So if we replace V and I with these I e to the st and V e to the st, and then we can figure out that the impedance of a capacitor, right? We solve everything through, we divide out the e to the st's, and then we get the voltage in terms of current. And so we got 1 divided by SC times I, which gives us our impedance of a capacitor to be 1 divided by SC. Right. And then lastly, for an inductor, we just proceed with those physical relationships. So we've got V is L di by dt. And so replacing everything through, we take the time derivative of this I e to the st, and S pops out, SL times I. So then that gives us the impedance of a capacitor of an inductor to be S times L. And these are all in the S domain, but we always take that S is j omega, where omega is our angular frequency and j is the imaginary number there. So that's for impedance. The last thing that we should talk about is power, and we're just going to be briefly introducing power. Not sure how much we're going to do with it this week, but I just wanted to talk about it. So given some periodic waveform, right? So this can be anything. This can be current, this can be voltage. Well, I guess that's all that we really look at, right? So any generic waveform x of t, with period capital T, It's helpful to discuss various properties of the waveform, such as the average or mean. And so to find the average, we usually denote this by these angle brackets here. You add up everything in the period and you divide by, how many points you have in the period. That's your average. So 1 divided by t times the integral over 1 period of that waveform. And it's also helpful to look at the root mean square. Root mean square. And we usually denote this with a capital, whatever the waveform symbol is, right? So if it's x, we do a capital X. If it's v, we do a capital B, v. So take the square root and we do this mean again. And we square the waveform there. And so the root mean square is usually a more appropriate measure when we have an alternating current that has some zero DC term, right? So you can imagine if we had a sine wave, right? So let's say that x of t is this sine wave. Well, the average value here is 0, right? So if we added up everything here over this one period, well, we've got positive half cycle and a negative half cycle, and it just sums up to be 0. But if we were to look at the RMS value, right, it would not be 0. You'd be squaring it, and you would be, taking that over one period. And when you square this, right, so this pops up and is scaled by some amount, and you're just finding the average of those two, right? So it actually squared, so it probably kind of looks more like that, and it'll end up being a little bit less than this peak there, but it'll be a positive value nonetheless, which is why root mean square is often a more appropriate measure for power through a resistive circuit especially. So I think with that, that's all I wanted to talk about here as far as from a theoretical standpoint. In the next video, I think we'll go over how to use a function generator. So see you guys next time. Thanks.